Hi everyone, Assalamualaikum warahmatullahi wabarakatuh. Welcome to watch the ANSYS CDF simulation video for subject Fluid Mechanic 2 from our group. First of all, I would like to introduce our members of group, which consists with 4 members. As the group leader, Muhammad Afiq bin Ismail will explain the topic of geometry details, simulation method, dimension and ANSYS CDF simulation. Next, Suhail Azmin will explain the theoretical and conclusion at the end of the presentation. Next, Jiha will explain the result, and the last one, me, Syima, will start with the introduction and objective of the study obtained. Okay, so I will start with introduction. There have 4 objectives that we will describe. First, to analyze the best result from the ANSYS simulation, which with this ANSYS simulation, we will able to find out if there is an error in a design. Second, to know animation from ANSYS simulation. This ANSYS simulation is run using software that allow us to see all the movement that occur when the measurement value has been set. So third, find the thermal boundary layer at the trailing edge. This is to ensure the boundary layer surface where the effect of viscosity is significant. And the last one, to know the different contour color from the flat surface. By knowing the color difference of each surface, we will know which part will facing the higher pressure.
Okay, next I will explain for the theory. Boundary layer is the layer of fluid in the immediate area of a bounding surface where the effects of viscosity are significant. The liquid or gas in the boundary layer tends to cling to the surface. For this boundary layer diagram, there are 3 regions in a boundary layer, namely lamina, turbulent and transition boundary region. In the lamina region, the direction of the velocity of the molecules is the same. In the turbulent region, the direction of the velocity of the molecule is different. The flow in such boundary layer is generally laminar at the leading or upstream portion and turbulent in the trailing or downstream portion. Okay, for thermal boundary layer, the fluid touching the surface is typically brought to rest by the shear stress at the wall when a fluid runs over a stationary surface, such as a flat plate, the bed of river or the pipe wall. Next, the area where flow changes from zero velocity at the wall to a maximum in the main line of the flow is known as the boundary layer. The free stream of fluid temperature approach to the plate at different temperature. Then the thermal boundary layer is generated. The thermal boundary layer exists only when the temperature of the free stream and the surface of the plate are not equal. Next is heat transfer. The overall heat transfer coefficient K is a measure of the resistance to heat flow, made up of the resistance caused by the plate material, amount of falling, nature of the fluids and type of exchanger used. Here are the unit of measurement in SI unit. And lastly, the roughness of the surface of solid plays a role. The flow velocity influences the heat transfer and especially the type of flow, whether it's laminar or turbulent.
Okay, first open ANSYS software, then go to toolbox, double click on fluid flow fluents. At the right, you need to click Analysis type 2D. Next, click Geometry and New Design Modeler Geometry. Okay, next select the unit and change to millimeter, and then click on XY plane. Make sure the plane in XY direction. Okay, next go to Sketching tab and modify. Select the rectangle. Okay, draw the rectangle on the sketching plan and set the dimension. V1 is for vertical, 20 mm, and H1 for horizontal, 200 mm. Now we need to convert it to 2D geometry. Go to Concept and Surface from Sketch. Using this concept, we can generate to 2D geometry. Click on the surface body, and now you can see the detail at the left corner. Okay, right now you need to change the surface body, change to fluid. So the software will analyze it as a fluid, and the geometry now is complete. Open the meshing workbench window, right click and click Edit. Okay, right now we need to generate mesh. By default, ANSYS have already his own mesh size. Now we need to generate the mesh by using the mesh setting. Right click on the mesh and generate mesh. Now this is the default mesh size, and we need to modify it. Go to element size and change to 0.001. Then generate the mesh again. Okay, now the mesh is generated, and okay, as you can see here, the mesh is very small and precise. You can see the statistic, the nodes and the elements. Now let's check the aspect ratio at the display style. Now you can see the mesh cells are not distributed properly in the sum region. Okay, now we need to use adaptive sizing to distribute the mesh uniformly through the geometry. Then generate the mesh again. Okay, right now the mesh is generated, and it seems it has already some distributed mesh. You also can check the skewness at the display style. Okay, right now we need to give name to the boundary style. First, you need to know the smart select, which is it will help you to define it. Select the bottom edge and click on create name selection and put the name of the boundary at selection name. Now you need to repeat this step at the top, left and right boundary. Okay, right now you can see all the name at the name selection at the left corner. The axis, the pipe wall, inlet and outlet. You need to reduce the error by click on mesh and update the generated mesh for your geometry. Now the mesh translation to Fluent was successful. Now we continue with setup the geometry. Right click on setup and edit. Click on double precision at Fluent Launcher. You need to wait until the ANSYS Fluid Solver window is open. Here you need to put all the necessary setup and all the boundary condition. you need to choose 2D space asymmetry and check the loaded mesh quality. Next, select the required flow model from the list. Choose the viscose and select the lamina. For the materials, load the fluid material from the Fluent database. Also, you need to change the material properties exactly like your current simulation, which is water. After you click H2O, which is water, now you can see the properties of the water at the bottom side. Here, you can see the basic information of the material, which is H2O water. Next, click on cell zone condition, which is surface body. Change the material name from air to water liquid. Click on operating condition and check the operating pressure, which is atmospheric pressure. It is a default pressure. Next, choose boundary condition. You can change the boundary condition type by yourself. Now, select velocity inlet boundary condition at the inlet. The value of velocity magnitude is 0.0005 meter per second. And press apply and close. For interior surface body, just maintain it. For the outlet, keep the default pressure for the outlet boundary. Just click OK. For the pipe wall, click Edit and see the stationary wall. No need to change it. Now, go to the solution and select the method. Pressure velocity coupling, select simple. For gradient, pressure and momentum, just maintain it. No need to change. Next, go to the monitor's residual. Here you need to change the X, Y and the continuity value, which is from 0.001 to 1 to the power of -6. Click on initialization and select the standard initialization. At the compute from, select the inlet and click initialization. Okay, next, click on run calculation and change the number of the iteration, which is from 0 to 1000 and click calculate. Here you will see the calculation will be calculated based on the data that you key in. Okay, right now the calculation is complete. Okay, now check the result by click on graphics and then contours. The variety of contour which is density, velocity, pressure and so on. Just select the velocity. As you can see in the picture, the maximum velocity is near at the center and decrease toward the pipe wall. You also can check the pressure. Now choose pressure, save. Here you can see the high pressure at the inlet and the low pressure, the blue color, at the outlet. Now let's check the velocity version along the central exit. From plot, select XY plot and select the velocity at the axis. Then click plot. From the graph, you can conclude it, the increase the position, the bigger the velocity magnitude.
For the result, insert contour 1, allocation periodic 1 shadow, the variable velocity, range global. Okay, as we can see, the minimum one is 0 and the maximum one is 0.1. The blue color stands for the minimum and the red color stands for the maximum. Here we can see field of colors and insert the counter, the number of counter 100. At the default legend view, at appearance, choose fix and the precision is 6. The font is sans serif. Color mode is default. Okay, then apply. Okay, at the contour 1, apply reflection or mirroring, and then for the method, choose ZX explain, and then apply. Okay. Right hand click at the contour 1 and duplicate, and rename it with contour 2. Add contour 2. Add contour 2, untick at the apply reflection, but then tick at the apply instancing transform and apply. So as we can see, it will form a square with a various color. Okay, untick at the contour 1 and contour 2. Then make a new wireframe and insert streamline 1. Right hand click at the streamline 1 and duplicate and rename it with streamline 2. At the streamline 2, apply reflection or mirroring, and the method, choose ZX explain. Okay, and we can see it will form a square like this. And then insert animation. Okay, we run it as animation. Okay, add animation. Choose sweep animation. Select streamline 1 and 2, and for the duration of animation, choose the slowest one. And then play the animation. So we can see the animation of ANSYS. Okay, before make a graph, create line first. At point 1, insert value 0.1. At point 2, insert value 0.1 and 0.02 to sketch the velocity profile on it, and then use this profile for estimation the boundary layer. Insert chart, location line 1, variable for x-axis, choose y, and variable for y-axis, choose velocity, then apply. Okay, for this figure, you can find the thermal boundary layer thickness and the velocity gradient at any location from the wall to the free stream. Turn on the line display, always on. Okay, here we can see the graph after we convert the ANSYS simulation to the graph.
And lastly, conclusion from our group is we totally done in our project. We are already explained all the process and solution in this video. Furthermore, we can go through in detail and understand how the flow project by ANSYS. All the result that we got from ANSYS, we can achieve our objective and solve the problem solving. Thank you.